Nanotechnology weapons. Nanotechnology weapons emerged not as a single invention, but as a gradual convergence of physics, chemistry, biology, and military research during the late 20th century. Their origins can be traced back to the early theoretical work on nanoscience in the 1950s, when physicist Richard Feynman introduced the idea that matter could be manipulated at the atomic scale. At the time, the concept was purely theoretical, but it quietly laid the foundation for one of the most transformative technological paths in modern history. By the 1980s and 1990s, advances in microscopy and material science made it possible to observe and manipulate structures measured in nanometers. Governments quickly recognized that controlling matter at this scale could fundamentally change medicine, industry, and warfare. Military research agencies, particularly in the United States, began funding classified projects exploring how nanomaterials could enhance armor, sensors, and weapon systems. These early efforts were framed as defensive innovations, but their potential offensive applications were evident from the start. Nanotechnology weapons differ from traditional arms because they do not rely on explosive force or visible destruction. Instead, they operate invisibly, interacting directly with biological systems, electronic components, or molecular structures. One of the earliest military interests involved nanomaterials capable of strengthening armor while remaining lightweight. This research influenced the development of advanced body armor and vehicle protection systems, changing how soldiers and machines could be deployed on the battlefield. As research progressed, attention shifted toward more controversial possibilities. Nanoparticles were found to have the ability to cross biological barriers, including the blood-brain barrier. This discovery revolutionized medicine, allowing targeted drug delivery, but it also raised serious concerns within defense communities. The same properties that allowed nanoparticles to treat disease could, in theory, be used to disrupt biological processes, interfere with cellular communication, or damage specific organs without leaving obvious traces. During the early 2000s, classified defense reports began discussing the strategic implications of nanotechnology in warfare. These documents described scenarios in which nanoscale devices could be used for surveillance, tracking, or sabotage. Unlike conventional weapons, such systems could be deployed covertly, remaining undetected while collecting data or influencing their environment. This marked a shift in military thinking, where control and precision became more valuable than brute force. Nanotechnology also influenced the development of autonomous systems. Sensors built with nanomaterials dramatically increased sensitivity and efficiency, allowing machines to detect chemical, biological, or radiological threats at previously impossible levels. This capability reshaped intelligence gathering and battlefield awareness, contributing to the rise of data-driven military operations. Ethical and legal concerns soon followed. Because nanotechnology weapons blur the line between civilian and military applications, regulating their use proved extremely difficult. Many nanotechnologies developed for peaceful purposes could be repurposed with minimal modification. This dual-use nature made transparency nearly impossible and pushed much of the research behind layers of classification and secrecy. International discussions on arms control struggled to address nanotechnology. Unlike nuclear or chemical weapons, nanoscale systems are hard to detect, monitor, or ban. Their components can be manufactured using civilian infrastructure, making enforcement unrealistic. As a result, nanotechnology quietly became embedded in modern military doctrine without clear public acknowledgement. Today, nanotechnology weapons are less about dramatic battlefield scenarios and more about subtle influence. They have shaped how militaries think about invisibility, precision, and long-term impact. Rather than replacing traditional weapons, nanotechnology integrates with them, enhancing efficiency and expanding strategic options. Its true significance lies not in a single device, but in how it has redefined the boundaries of what a weapon can be. The development of nanotechnology weapons reflects a broader transformation in warfare itself. Power is no longer measured only by explosive yield or troop numbers, but by control at the smallest possible scale. In this sense, nanotechnology represents a quiet revolution, one that continues to evolve largely unseen, shaping the future of conflict in ways that are difficult to observe, measure, or fully understand. Project Thor. Rods from God. Project Thor, more commonly known as rods from God, is a theoretical weapons concept that emerged during the Cold War era, at a time when military strategists were actively exploring ways to extend warfare beyond Earth's atmosphere. Its origins are closely tied to the development of space technology in the late 1950s and 1960s, when satellites first demonstrated that orbit could be used not only for observation and communication, but potentially for direct military action. The idea behind Project Thor was deceptively simple. Instead of using nuclear warheads, a weapon could rely purely on kinetic energy. Dense metal rods, typically proposed to be made of tungsten due to its extreme hardness and high melting point, would be placed in orbit. When released, these rods would fall toward Earth at tremendous speed, guided by gravity and minimal course correction. Upon impact, the energy released would rival that of a small nuclear weapon, but without radiation, fallout, or long-term environmental contamination. The concept gained attention in military research circles during the 1980s, particularly within discussions surrounding space-based defense systems. Advances in orbital mechanics, guidance systems, and material science made the idea technically plausible, even if prohibitively expensive. Tungsten, while difficult to work with, offered ideal properties. It could withstand intense heat during atmospheric entry and deliver devastating force upon impact. Project Thor represented a shift in strategic thinking. Nuclear weapons had become politically dangerous to use due to their catastrophic consequences and global implications. A kinetic weapon, by contrast, could achieve precise destruction of hardened targets such as underground bunkers, missile silos, or command centers, without crossing the psychological and political threshold associated with nuclear strikes. This made the concept appealing to military planners seeking dominance without escalation. Despite its theoretical advantages, Project Thor faced significant technical challenges. Maintaining weapons platforms in orbit would require constant monitoring and protection from space debris, enemy interference, or mechanical failure. Guidance accuracy was another concern. Even small deviations in trajectory could result in missing a target by kilometers, especially when launched from orbit. During the late 20th century, the required precision remained beyond practical reach. International law also played a role in limiting development. Treaties such as the Outer Space Treaty of 1967 prohibited the placement of weapons of mass destruction in orbit. While kinetic weapons did not technically fall under the definition of nuclear or chemical arms, their destructive potential raised serious legal and ethical questions. This ambiguity pushed the concept further into classified discussions rather than public programs. In the early 2000s, interest in Project Thor quietly resurfaced as guidance systems, satellite control, and real-time targeting improved dramatically. Advances in GPS, artificial intelligence, and sensor technology reduced many of the limitations that once made orbital kinetic weapons impractical. At the same time, global military strategy increasingly emphasized rapid response and precision strikes, aligning well with the theoretical strengths of rods from God. The psychological impact of such a weapon also became a subject of analysis. A strike arriving from space without warning, explosion, or missile launch would fundamentally alter how nations perceived vulnerability. Traditional early warning systems, designed to detect missile launches, would offer little protection. This aspect alone made Project Thor strategically unsettling, even as a purely conceptual threat. While no public evidence confirms the deployment of operational rods from God, the concept has influenced modern military doctrine in subtle ways. It reinforced the idea that space is not merely a support domain, but a potential battlefield. It also contributed to the growing emphasis on non-nuclear strategic weapons capable of decisive force. Project Thor remains a symbol of how future warfare may rely less on visible firepower and more on physics itself. By turning gravity into a weapon, the concept reflects a broader trend in military innovation, achieving maximum impact with minimal signature. Whether or not it is ever realized, Project Thor continues to shape how military planners imagine conflict in an era where the boundary between Earth and space is no longer a barrier, but an opportunity. Active Denial System. The Active Denial System, often abbreviated as ADS, emerged from a long-standing military interest in non-lethal weapons designed to control crowds and limit escalation without resorting to conventional firearms. Its development began in the late 1990s, When defense researchers in the United States sought alternatives to tear gas, rubber bullets, and other methods that had proven unreliable or politically controversial in modern conflict zones. At its core, the active denial system is based on directed energy. It emits a focused beam of millimeter-wave radiation, operating at a frequency that penetrates only the outermost layer of human skin. When a person is exposed to the beam, the energy rapidly heats the water molecules in the skin's surface, creating an intense burning sensation. This effect is designed to be immediately intolerable, forcing individuals to move away from the source almost instantly. The scientific foundation of ADS rests on decades of research into electromagnetic radiation and its interaction with biological tissue. Millimeter waves were already well understood in telecommunications and atmospheric science. What made ADS distinctive was the precise calibration of power, frequency, and exposure time. The system was engineered to cause pain without causing permanent injury, burns, or cellular damage when used within operational limits. Development accelerated in the early 2000s under the supervision of the U.S. Department of Defense. Field tests demonstrated that subjects exposed to the beam instinctively withdrew within seconds, often describing the sensation as unbearable heat rather than physical impact. This immediate response distinguished ADS from traditional crowd control tools, which often required repeated use or direct physical contact. The active denial system influenced military thinking by introducing the concept of pain as a controllable, reversible weapon. Unlike firearms or explosives, ADS left no visible marks, no blood, and no lasting environmental damage. From a strategic standpoint, this reduced the political cost of using force in sensitive situations such as peacekeeping operations, embassy protection, and urban security. Despite its classification as non-lethal, ADS sparked intense ethical debate. Critics argued that the invisibility of the beam made it psychologically disturbing. Individuals targeted by the system could not see or understand what was affecting them, creating fear and confusion. Human rights organizations questioned whether such weapons could be misused for coercion, punishment, or suppression without accountability. Operational challenges also limited widespread deployment. The system requires significant power and line-of-sight targeting, making it less effective in complex urban environments or adverse weather conditions. Rain, fog, and physical obstacles can reduce its range and effectiveness. These limitations reinforced its role as a specialized tool rather than a universal solution. Over time, research into ADS contributed to broader advancements in directed energy technology. Lessons learned from controlling beam intensity, managing thermal effects, and ensuring operator safety informed later developments in microwave and laser-based systems. In this sense, ADS functioned not only as a weapon but also as a technological stepping stone. The existence of the active denial system altered public perception of future warfare. It demonstrated that force no longer had to be destructive to be effective. Control, deterrence, and compliance could be achieved through discomfort rather than injury. This concept quietly reshaped discussions about how governments might manage unrest and conflict in increasingly urbanized societies. Today, the active denial system stands as a transitional technology. It occupies the space between traditional weapons and psychological influence tools, relying on physics rather than violence to achieve its purpose. Its legacy lies in how it reframed the use of energy as a direct means of control, signaling a future where power is exerted not through visible destruction, but through precise and temporary manipulation of human sensation. DARPA Insect Allies. The DARPA Insect Allies program emerged in the mid-2010s as part of a broader effort to explore unconventional methods of biological intervention. Officially, the program was presented as a defensive agricultural initiative aimed at protecting crops from natural threats such as drought, disease, and environmental stress. However, the underlying concept immediately attracted global attention due to its unusual and potentially dual-use nature. At the heart of the program was a novel idea: using insects as delivery systems for genetically engineered viruses. These viruses were designed to alter the genetic expression of plants directly in the field, rather than through traditional breeding or laboratory modification. By releasing insects carrying these viruses, large areas of crops could theoretically be modified quickly and with precision. The scientific basis for insect allies was rooted in advances in gene editing technologies, particularly CRISPR-based systems. These tools made it possible to change how specific genes function without permanently altering the plant's DNA. From a civilian perspective, this offered a powerful solution to agricultural crises. Crops facing sudden threats could be rapidly updated to resist disease or tolerate extreme weather. Military and security analysts, however, viewed the program through a different lens. The same mechanism that allowed crops to be protected could also be used to damage or disrupt agricultural systems. Insects, unlike conventional delivery methods, are difficult to track, contain, or attribute. This raised concerns that the technology could be repurposed for covert biological interference without clear evidence of origin. The involvement of DARPA, an agency known for high-risk, high-impact military research, further intensified scrutiny. While DARPA emphasized transparency and compliance with international conventions, the program structure highlighted the blurred boundary between defense and offense in modern biological research. Unlike traditional biological weapons, insect allies relied on subtle genetic influence rather than immediate destruction. The program influenced international discussions on biosecurity and warfare. Several scientists and policy experts argued that insect allies challenged existing arms control frameworks, which were not designed to regulate gene editing technologies deployed through natural vectors. This gap in regulation revealed how rapidly biotechnology was outpacing legal and ethical oversight. From a technological standpoint, insect allies demonstrated how warfare concepts were shifting toward indirect impact. Instead of targeting populations or infrastructure directly, future conflicts could focus on food systems, supply chains, and ecological stability. Agriculture, once considered a civilian domain, became recognized as a strategic vulnerability. The public debate surrounding insect allies had lasting consequences. It prompted increased calls for transparency in government-funded biological research and greater international cooperation on genetic technology oversight. At the same time, it accelerated research into detection and monitoring of gene-edited organisms in the environment. Today, DARPA Insect Allies is remembered less for its stated goals and more for what it revealed about the future of conflict. It showed how biological systems could be influenced quietly, efficiently, and at scale. The program stands as an example of how emerging technologies can redefine the concept of a weapon, not through overt violence, but through controlled manipulation of life itself. Project Blue Beam. Project Blue Beam is not a conventional weapons program documented through declassified military archives. Instead, it exists at the intersection of advanced technology, psychological operations, and modern conspiracy culture. The concept first gained public attention in the early 1990s, when it was described as a hypothetical government-led project aimed at manipulating mass perception on a global scale. While its existence has never been officially confirmed, the ideas associated with Project Blue Beam reflect real technological developments and long-standing military interest in perception management. The origins of the concept are closely linked to the evolution of psychological warfare. Throughout the 20th century, governments increasingly recognized that controlling information and perception could be as powerful as controlling territory. Radio broadcasts, propaganda films, and later television became tools for shaping public opinion during wartime. By the late Cold War period, attention shifted toward more sophisticated methods that could influence entire populations simultaneously. Project Blue Beam is most commonly described as a multi-stage operation involving advanced holographic projection, satellite-based imagery, and electromagnetic technologies. According to the theory, these tools could be used to project large-scale visual phenomena into the sky, creating the illusion of extraordinary events. While such descriptions are often dismissed as speculative, they are rooted in real advancements in optics, projection systems, and satellite coordination. The technological foundation behind the idea began forming decades earlier. By the 1970s and 1980s, military and space agencies were experimenting with high-resolution satellite imaging, laser projection, and atmospheric light manipulation. These technologies were initially developed for navigation, communication, and surveillance. However, their potential for psychological impact became increasingly apparent as display systems grew more realistic and immersive. Project Blue Beam is often associated with the concept of simulated global events designed to unify or destabilize populations. From a strategic standpoint, the ability to create a shared visual experience across vast regions would represent an unprecedented level of influence. Unlike traditional media, which relies on screens and devices, such an approach would bypass conventional channels and present information directly within the physical environment. The theory also reflects growing awareness of how belief systems can be shaped through sensory input. Studies in neuroscience and psychology have shown that visual stimuli, when combined with emotional context, can override rational skepticism. Military planners have long studied these effects in smaller-scale operations, such as battlefield deception and morale disruption. Project Blue Beam extrapolates these principles to a global scale. During the late 20th century, governments began investing heavily in information dominance. The rise of real-time global broadcasting, satellite networks, and digital communication transformed how events were perceived and interpreted. This environment made large-scale psychological operations more feasible than ever before. Project Blue Beam emerged within this context as a symbolic representation of ultimate informational control. Public discussion of Project Blue Beam intensified alongside the expansion of space-based infrastructure. Satellites capable of precise positioning, synchronized timing, and global coverage became central to modern civilization. Navigation systems, weather monitoring, and telecommunications demonstrated how deeply space technology had integrated into everyday life. This integration fueled speculation that the same systems could be repurposed for mass perception manipulation. From a military theory perspective, Project Blue Beam represents a shift away from physical destruction toward cognitive influence. Instead of targeting infrastructure or armed forces, such an operation would target belief, trust, and collective interpretation of reality. This aligns with documented doctrines emphasizing psychological dominance as a force multiplier. Critics of the concept argue that the technical challenges of creating convincing large-scale illusions remain prohibitive. Atmospheric conditions, geographic variation, and human perception impose significant limitations. Nevertheless, partial implementations of similar ideas already exist. Large-scale drone light displays, augmented reality systems, and advanced projection mapping demonstrate that coordinated visual manipulation is technologically achievable on a limited scale. The cultural impact of Project Blue Beam is significant regardless of its factual status. It reflects widespread anxiety about the power of governments and institutions to shape reality through technology. As digital environments become more immersive and indistinguishable from physical experience, the boundary between perception and manipulation continues to blur. In this sense, Project Blue Beam functions as both a theory and a warning. It encapsulates fears about centralized control over information, technology, and belief. Whether or not such a project exists as described, the technologies associated with it are real, and their influence on human perception is undeniable. Project Blue Beam remains a powerful narrative because it addresses a fundamental shift in modern power structures. Control is no longer exercised solely through force or law, but through the ability to define what people see, hear, and believe. In the future of conflict, dominance may depend less on weapons that destroy cities and more on systems that reshape reality itself. Autonomous killer drones. Autonomous killer drones emerged as a direct result of rapid advancements in artificial intelligence, robotics, and remote warfare during the late 20th and early 21st centuries. Their conceptual roots can be traced back to early unmanned aerial vehicles, originally designed for reconnaissance and surveillance. These early drones removed pilots from physical danger, but decision-making authority remained firmly in human hands. The turning point came with the exponential growth of machine learning and real-time data processing. As algorithms became capable of recognizing patterns, identifying objects, and adapting to complex environments, military planners began exploring systems that could operate with minimal or no human intervention. The goal was efficiency, speed, and operational dominance in environments where human reaction time was insufficient. Autonomous killer drones differ from remotely piloted systems in a fundamental way. They are designed to select, track, and engage targets independently, based on predefined parameters and sensor input. This autonomy allows them to function in communication-denied environments, where signals can be jammed or delayed. From a strategic perspective, this removed one of the major vulnerabilities of earlier drone warfare. The development of these systems was heavily influenced by modern battlefield realities. Conflicts increasingly took place in urban environments, with rapidly changing conditions and asymmetric threats. Human operators, often located thousands of kilometers away, struggled to interpret incomplete data under time pressure. Autonomous systems promised faster decision cycles and continuous operational presence. Early prototypes focused on defensive applications, such as automated perimeter security and missile interception. Over time, offensive capabilities expanded. Advances in computer vision enabled drones to distinguish vehicles, weapons, and human movement patterns. Sensor fusion combined visual, infrared, radar, and acoustic data into a single operational picture, allowing drones to make complex assessments in real time. The rise of autonomous killer drones also reshaped military doctrine. Traditional chains of command were designed around human judgment and accountability. Introducing machines capable of lethal decisions challenged these structures. Military institutions responded by embedding rules of engagement directly into software, translating legal and ethical constraints into code. International concern grew as these technologies matured. Unlike nuclear weapons, autonomous drones require relatively modest industrial infrastructure. This lowered the barrier to entry and increased the risk of proliferation. Once developed, software-based autonomy could be replicated and modified with ease, making containment extremely difficult. Testing and deployment occurred gradually, often under conditions of limited transparency. Autonomous features were introduced incrementally, blurring the line between human-assisted and fully autonomous operation. This gradual integration made it difficult to pinpoint when machines truly crossed the threshold into independent lethal agents. Beyond their physical impact, autonomous killer drones influenced the psychological landscape of warfare. The presence of machines capable of persistent surveillance and sudden action altered how adversaries perceived safety and control. The battlefield became less predictable, governed by algorithms rather than human intuition. The existence of autonomous killer drones also accelerated broader automation trends within the military. Logistics, intelligence analysis, and strategic planning increasingly relied on AI-driven systems. Lethal autonomy became part of a larger transformation in how wars were prepared and conducted. Today, autonomous killer drones represent a fundamental shift in the nature of conflict. They embody a transition from human-centered warfare to systems-driven confrontation. Their significance lies not only in what they can destroy, but in how they redefine responsibility, speed, and control in military operations. As decision-making moves from human minds to machine processes, the character of warfare itself continues to change in quiet but irreversible ways. Hypersonic glide vehicles. Hypersonic glide vehicles, often abbreviated as HGVs, emerged from decades of research into missile technology, aerodynamics, and strategic deterrence. Their origins can be traced back to the Cold War, when major powers began searching for ways to overcome increasingly sophisticated missile defense systems. Traditional ballistic missiles followed predictable trajectories, making them vulnerable to interception as detection and tracking technologies improved. Early research into hypersonic flight began in the 1950s and 1960s, driven by experimental aircraft programs and reentry vehicle studies. Scientists sought to understand how objects behave at speeds exceeding Mach 5, where air resistance, heat, and pressure behave in extreme and often counterintuitive ways. These studies laid the groundwork for later concepts that combined speed with maneuverability. Unlike conventional ballistic warheads, hypersonic glide vehicles are launched into the upper atmosphere by rockets and then separate from their boosters. Instead of following a simple arc through space, they re-enter the atmosphere and glide at hypersonic speeds toward their targets. This gliding phase allows them to maneuver unpredictably, changing altitude and direction while maintaining extreme velocity. The strategic significance of HGVs lies in this combination of speed and control. Traveling at several kilometers per second, they drastically reduce the time between launch and impact. At the same time, their ability to maneuver makes them difficult to track and intercept. Existing missile defense systems, designed to predict ballistic paths, struggle to respond effectively to such dynamic threats. Interest in hypersonic glide vehicles intensified in the late 20th and early 21st centuries as advances in materials science made sustained hypersonic flight more feasible. New heat-resistant composites and thermal protection systems allowed vehicles to survive the immense friction generated during atmospheric travel. Without these breakthroughs, prolonged hypersonic gliding would have remained purely theoretical. From a military planning perspective, HGVs represented a shift in deterrence logic. Nuclear weapons had long relied on assured retaliation, but hypersonic systems introduced uncertainty. Their speed and low-altitude flight profile reduced early warning times, complicating decision-making for targeted nations. This uncertainty alone became a strategic factor, influencing global stability. The development of HGVs also reflected a broader trend toward precision strike capabilities. Unlike earlier strategic weapons designed for large-area destruction, hypersonic vehicles could be guided with increasing accuracy. This made them suitable for targeting hardened or time-sensitive objectives, such as command centers or mobile assets, without relying on massive explosive yields. Testing programs revealed both the promise and difficulty of the technology. Maintaining control at hypersonic speeds requires constant adjustment, as even minor atmospheric variations can affect trajectory. Guidance systems had to process data and react almost instantaneously, pushing the limits of onboard computing and sensor integration. Beyond their immediate military application, hypersonic glide vehicles influenced international security dynamics. Their emergence prompted renewed discussions about arms races and strategic balance. Unlike traditional weapons, hypersonic systems blurred the line between conventional and nuclear delivery platforms, creating ambiguity about intent during launch detection. The secrecy surrounding HGV development further amplified their impact. Limited public information and classified test results fueled speculation and concern among analysts and policymakers. This opacity became part of the weapon's strategic value, as uncertainty itself served as a deterrent. Today, hypersonic glide vehicles stand as a defining feature of modern strategic warfare. They embody a shift towards speed, unpredictability, and technological complexity. Rather than replacing existing weapons, they alter the environment in which all strategic systems operate. Their true influence lies not only in their destructive potential, but in how they compress time, destabilize certainty, and reshape the calculus of global power. Voice of God weapon. The concept commonly referred to as the voice of God weapon emerged from long-standing military and scientific interest in the relationship between sound, electromagnetic waves, and human perception. Its origins are not tied to a single laboratory or official program, but rather to a gradual accumulation of research in acoustics, neuroscience, and directed energy technologies throughout the 20th century. Early foundations were laid during World War II and the Cold War, when governments began systematically studying psychological warfare. Military strategists recognized that fear, confusion, and belief could influence outcomes as effectively as physical force. Loudspeakers, radio broadcasts, and sonic intimidation techniques were among the first tools used to shape enemy morale. These early methods, however, relied on conventional sound propagation and were limited by distance, environment, and visibility. As research progressed, attention turned to more precise ways of delivering sound. By the 1960s and 1970s, scientists were studying how electromagnetic waves interact with the human nervous system. Experiments revealed that under certain conditions, microwave frequencies could induce auditory sensations inside the human head without using external speakers. This phenomenon, later known as the microwave auditory effect, demonstrated that sound perception could be generated directly within the brain. This discovery had immediate implications beyond medicine and communications. If sound could be perceived without passing through the ears, it could theoretically be delivered selectively, silently, and invisibly. Military researchers began exploring whether such effects could be controlled, directed, and scaled. The possibility of transmitting voices or sounds directly to individuals raised profound strategic and psychological questions. By the late Cold War period, classified research into directed energy systems expanded. Technologies such as focused microwave emitters and acoustic waveguides were examined for non-lethal applications. Official documentation framed these studies around crowd control, disorientation, and behavioral influence. However, the underlying capability suggested something more subtle: direct manipulation of perception. The idea of a voice of God weapon emerged as a way to describe this capability in cultural and analytical discussions. The term reflected the potential psychological impact of hearing a voice that appeared to come from nowhere, without an identifiable source. Such an experience could be deeply unsettling, particularly in high-stress environments such as battlefields or civil unrest. From a psychological standpoint, auditory perception is closely tied to authority and belief. Human brains are conditioned to respond instinctively to voices, especially commands or warnings. Research in cognitive science showed that auditory stimuli can bypass rational filtering more easily than visual information. This made sound-based influence an attractive area of study for psychological operations. The strategic value of such a system lay in its deniability. Unlike traditional weapons, a directed auditory effect would leave no physical evidence. Targets might experience confusion, fear, or altered behavior without understanding the cause. This ambiguity complicated attribution and accountability, making such technologies difficult to regulate under existing military frameworks. Advancements in signal processing and miniaturization during the late 20th and early 21st centuries further increased feasibility. More efficient emitters, improved targeting systems, and refined control over waveforms allowed greater precision. While no public confirmation exists of operational deployment, these technological trends reinforce speculation about practical implementation. The concept also influenced broader discussions about the future of warfare. As conflicts increasingly moved into urban and civilian spaces, the ability to influence behavior without visible violence became strategically appealing. Control through perception aligned with emerging doctrines emphasizing information dominance and psychological superiority. Ethical concerns accompanied these developments. The possibility of directly influencing thoughts or perceptions challenged established norms around consent and human autonomy. Unlike traditional psychological operations, which rely on persuasion and messaging, directed auditory influence operates below conscious awareness, raising questions about its long-term effects on mental health and trust. Today, the voice of God weapon remains a symbol rather than a confirmed system. Its significance lies not in documented battlefield use, but in what it represents: the transformation of warfare from physical confrontation to cognitive influence. It illustrates how modern power increasingly operates within the human mind, using technology to shape experience rather than destroy structures. In this sense, the voice of God concept reflects a broader evolution in conflict. As tools become quieter, more precise, and less visible, the battlefield expands beyond geography into perception itself. The voice, once a natural human instrument, becomes a potential vector of control, silent, targeted, and profoundly influential. Project Maven. Project Maven emerged in the mid-2010s as a response to a fundamental problem facing modern militaries: the overwhelming volume of data generated by contemporary warfare. Drones, satellites, and surveillance platforms were collecting more video and imagery than human analysts could realistically process. The challenge was no longer gathering information, but understanding it fast enough to act. The project was officially launched by the U.S. Department of Defense in 2017 under the name Algorithmic Warfare Cross-Functional Team. Its purpose was to integrate artificial intelligence into military intelligence workflows, beginning with automated analysis of full-motion video from unmanned aerial systems. The name Maven symbolized expertise, an artificial analyst capable of extracting meaning from raw data. Before Project Maven, intelligence analysis relied heavily on human attention. Analysts were required to watch hours of video footage to identify objects, movements, and patterns. This process was slow, exhausting, and prone to error. As drone usage expanded across multiple theaters of operation, the imbalance between data collection and analysis became strategically dangerous. Advances in machine learning offered a solution. Computer vision algorithms had already demonstrated the ability to recognize faces, vehicles, and objects in civilian applications. Project Maven adapted these technologies for military use, training algorithms to detect and classify objects of interest such as vehicles, buildings, and human activity within aerial footage. The introduction of AI into intelligence analysis marked a turning point. Instead of replacing human analysts, Project Maven was designed to augment them. Algorithms filtered vast datasets, highlighting relevant segments and reducing cognitive overload. This allowed analysts to focus on interpretation and decision-making rather than raw observation. Project Maven also influenced how military institutions understood the role of artificial intelligence. AI was no longer seen as a distant or experimental technology, but as an operational tool integrated into real-world missions. This shift accelerated broader adoption of AI across defense systems, including logistics, threat assessment, and strategic planning. The project quickly became a focal point of ethical and public debate. Concerns were raised about the role of private technology companies in military applications and the potential for AI to contribute to lethal decision-making. These discussions highlighted a growing tension between technological capability and societal values. From a strategic perspective, Project Maven represented a move toward algorithmic warfare. Speed became a decisive factor. By compressing the time between observation and action, AI-driven analysis altered the tempo of military operations. Decisions that once took hours could now be made in minutes. The project also revealed the growing dependency of modern warfare on data quality. AI systems are only as effective as the information they receive. This increased the importance of sensor accuracy, data integrity, and protection against deception. Information itself became a contested domain. Beyond its immediate objectives, Project Maven reshaped how intelligence was conceptualized. Intelligence was no longer just a human activity, but a collaboration between analysts and machines. Trust shifted gradually from individual judgment to system-assisted evaluation. Today, Project Maven stands as a defining moment in the evolution of AI-enabled warfare. It demonstrated how artificial intelligence could be embedded into the core of military decision-making without direct human removal from the process. Its legacy lies in how it normalized algorithmic assistance as a standard component of modern conflict. Project Maven reflects a broader transformation in power dynamics. Those who can process information fastest gain strategic advantage. In this environment, intelligence is not just about seeing more, but about understanding sooner. The battlefield becomes a data stream, and control depends on the ability to interpret it before anyone else. Psychotronic weapons. Psychotronic weapons are described as systems intended to influence human perception, cognition, or emotional state through directed energy, electromagnetic fields, or other non-traditional physical mechanisms. Unlike conventional weapons, which act through mechanical or chemical force, psychotronic concepts focus on interaction with the nervous system. The term itself gained visibility during the Cold War, when both Western and Eastern Bloc researchers explored the boundaries between physics, biology, and psychology. The intellectual roots of psychotronic theory lie in early research on bioelectromagnetics. During the first half of the 20th century, scientists discovered that the human nervous system operates through electrical signals. Brain activity, muscle control, and sensory perception all depend on measurable electrical patterns. This realization led to a parallel question within defense research circles. If biological systems are electrical, could they be externally influenced by controlled electromagnetic exposure? By the 1950s and 1960s, military-funded laboratories began systematic studies on how radiofrequency and microwave radiation affected biological tissue. Most of this work focused on safety limits for radar operators and communications personnel. However, side observations suggested that certain frequencies and modulation patterns could alter mood, alertness, or cognitive performance under controlled conditions. These findings did not produce immediate weapons, but they established a research direction. The word psychotronic became associated particularly with Eastern European and Soviet-era research programs that investigated mind-energy interaction and electromagnetic biological effects. Declassified fragments and secondary reports indicated sustained interest in how fields and waves might influence neural processes. While documentation remains incomplete, the persistence of these programs shaped Western threat assessments and fueled reciprocal research. During the Cold War, intelligence agencies treated cognition as a strategic domain. Psychological warfare units already used messaging, sound, and visual stimuli to influence behavior. Psychotronic concepts extended this logic into the physical layer of neural function. Instead of persuasion through content, influence would occur through signal exposure. This distinction marked a conceptual shift from informational to physiological psychological operations. Technological progress in signal generation strengthened theoretical feasibility. More precise transmitters, phased arrays, and frequency control systems enabled tightly defined electromagnetic outputs. Laboratory experiments demonstrated that neural activity could be measured and categorized with increasing accuracy using electroencephalography and later imaging techniques. Mapping brain patterns made the idea of targeted interference appear more structured, even if still largely experimental. Strategic analysis during the late 20th century treated psychotronic weapons as a potential asymmetrical tool. A system capable of degrading concentration, inducing disorientation, or altering emotional stability without visible injury would operate below the threshold of conventional warfare. This ambiguity made attribution and response difficult, which in itself was seen as a strategic advantage. Scientific consensus, however, remained cautious. Many claimed effects were inconsistent, weak, or highly dependent on individual variability. Reproducibility proved to be a major barrier. Human neurobiology is complex, and externally induced changes were difficult to control with precision. As a result, much of the research stayed exploratory rather than operational. Even without confirmed deployment, the concept of psychotronic weapons influenced defense planning and public discourse. It expanded the recognized battlespace to include the human nervous system as a potential target surface. Military doctrine gradually incorporated the broader idea that cognitive and neurological performance could be contested through technology. Ethical and legal implications followed naturally. Traditional arms control frameworks are built around measurable harm and physical damage. Systems aimed at perception and cognition challenge those definitions. Effects may be temporary, subjective, or difficult to prove, complicating oversight and regulation. This regulatory gap contributed to continued secrecy around related research. In modern strategic thought, psychotronic weapons represent a category defined more by intent than by confirmed hardware. They illustrate the trajectory of military innovation towards subtle, non-visible influence mechanisms. Rather than destroying infrastructure, such systems would seek to shape human experience directly. The emphasis shifts from territory to perception, from impact to internal state. Today, psychotronic weapons remain controversial and partially theoretical, but their conceptual importance is clear. They reflect an enduring military interest in the interface between technology and the human mind. Whether realized as practical systems or not, they mark a stage in the evolution of warfare where influence over cognition is considered alongside control of land, air, sea, space, and data. Laser weapons systems. Laser weapons systems emerged from the long evolution of directed energy research, combining advances in physics, optics, and power engineering into a new class of military technology. Unlike conventional weapons that rely on projectiles or explosives, laser systems deliver energy at the speed of light, concentrating it into a narrow, controlled beam. Their development reflects a steady shift in military science toward precision, efficiency, and minimal delay between targeting and effect. The scientific foundation for laser weapons was established in 1960 with the first working laser device. Early lasers were laboratory instruments, fragile and energy-intensive, but their properties immediately attracted defense interest. A beam that could travel in a straight line, maintain tight focus, and deliver concentrated energy over distance suggested future tactical applications. Initial military research focused on ranging, targeting, and guidance, where lasers proved highly effective. During the Cold War, directed energy concepts gained strategic attention. Defense programs explored whether lasers could disable sensors, intercept missiles, or damage equipment without explosive force. Early prototypes faced severe limitations. Power generation, beam stability, and atmospheric distortion reduced effectiveness. Large systems required bulky chemical fuel sources or massive electrical infrastructure, preventing practical deployment. Despite these obstacles, research continued steadily. Improvements in solid-state lasers, fiber lasers, and adaptive optics gradually increased efficiency and reliability. By the late 20th century, beam control and thermal management technologies had matured enough to support sustained testing outside laboratory conditions. These advances transformed lasers from experimental curiosities into viable tactical tools. Laser weapons systems influenced military thinking because they changed the economics of engagement. Traditional interceptors require physical ammunition and complex logistics. A laser, once powered, can fire repeatedly with minimal per-shot cost. This property made laser defense especially attractive against high-volume threats such as drones, rockets, and small projectiles. Instead of matching each incoming threat with another missile, a single energy system could respond continuously. Operational concepts evolved around this advantage. Naval platforms became early candidates for deployment because ships can generate large amounts of electrical power. Ship-based laser systems were tested for point defense, targeting small airborne threats at short to medium range. The controlled environment and stable power supply improved performance compared to mobile ground units. Another defining characteristic of laser weapons is precision. The beam can be adjusted in duration and intensity, allowing operators to scale effects from sensor disruption to structural damage. This tunable output aligned with doctrines emphasizing proportional response and controlled escalation. Rather than destroying entire targets, lasers could disable critical components. Atmospheric interaction remained a central technical challenge. Dust, moisture, turbulence, and heat gradients distort beams and reduce range. Military research addressed this through adaptive optics and real-time beam correction, techniques originally developed for astronomical observation. These corrections allowed lasers to maintain focus through imperfect atmospheric conditions, extending practical engagement distances. Laser weapons systems also reshaped defensive strategy. Instead of relying solely on armor and interception, platforms could actively neutralize threats before impact. This layered defense approach increased survivability for ships, vehicles, and installations. Speed became the decisive factor. Because a laser strike arrives almost instantly, it reduces reaction windows for incoming threats. The psychological dimension of laser weapons is distinct. Engagement occurs silently and invisibly across most of the beam's path. Targets may be damaged without warning sounds or visible projectiles. This subtlety changes how force is perceived, replacing explosive events with controlled energy transfer. The absence of traditional firing signatures complicates detection and attribution. As power systems improved in the early 21st century, laser weapons transitioned from experimental demonstrations to limited operational deployment. Compact high-energy lasers became feasible for vehicles and aircraft, though with range and duration constraints. Integration required redesigning cooling systems, power distribution, and targeting sensors to support sustained operation. Laser weapon systems represent a broader transformation in how military force is delivered. Energy replaces mass as the carrier of effect. Engagement becomes a function of electrical capacity and beam control rather than ammunition supply. This transition aligns with wider trends in automation, sensing, and precision targeting. Today, laser weapons stand as a mature example of directed energy warfare moving into practical use. Their significance lies not only in their technical performance, but in how they alter engagement logic. They compress time between decision and outcome, reduce logistical burden, and enable finely controlled application of force. In doing so, they mark a clear step toward a future where energy itself becomes the primary instrument of defense and attack. Weather warfare programs. Weather warfare programs refer to military and state-sponsored efforts to understand, influence, or strategically exploit atmospheric processes for operational advantage. Unlike conventional weapons development, this field grew from scientific meteorology and climate research, gradually intersecting with defense planning as governments recognized how strongly weather affects logistics, visibility, mobility, and timing in warfare. The roots of weather modification research extend back to the early 20th century, when scientists began systematic study of cloud formation and precipitation. By the 1940s, experimental cloud seeding demonstrated that introducing certain particles, such as silver iodide, into clouds could encourage rainfall under specific conditions. What began as a civilian scientific experiment quickly attracted military interest, since even small shifts in weather could influence battlefield outcomes. During the Cold War, weather became recognized as a strategic variable rather than a background condition. Military planners increasingly relied on forecasting models and atmospheric data to guide operations. At the same time, classified research explored whether limited, localized weather modification might be achievable on demand. The objective was not global climate control, but tactical environmental shaping. One of the most historically documented examples of operational weather modification occurred during the Vietnam War. A classified program conducted cloud seeding over targeted regions to extend monsoon rainfall and degrade transportation routes. The operational logic was simple. Heavier and longer-lasting rain would slow movement and reduce supply efficiency. This program demonstrated that weather intervention could move from theory into field use, even if results were variable. Scientific progress in atmospheric physics during the late 20th century deepened military understanding of environmental systems. Satellites, radar networks, and global sensing platforms created detailed models of weather behavior. With improved measurement came renewed interest in influence. Defense research agencies examined whether electromagnetic energy, ionospheric heating, or aerosol dispersion could produce measurable atmospheric effects. Weather warfare programs influenced doctrine by expanding the definition of the battle space. The environment itself became a factor that could potentially be shaped rather than merely endured. Control over terrain had always been central to strategy. The possibility of influencing atmospheric conditions suggested a new layer of control above the terrain. Technical limitations remained significant. Weather systems are complex, nonlinear, and sensitive to countless variables. Small interventions often produce unpredictable outcomes. This unpredictability limited operational reliability and made large-scale control impractical. Nevertheless, even partial or localized influence retained strategic value in planning scenarios. International concern about environmental modification led to diplomatic response. In the late 1970s, global agreements were established to prohibit hostile use of environmental modification techniques on a large scale. These agreements acknowledged that environmental manipulation, if weaponized, could have widespread and uncontrollable consequences. The legal framework did not eliminate research, but it shaped how programs were defined and disclosed. The perception of weather as a potential weapon also affected public and analytical discourse. As sensing and modeling technologies improved, so did awareness of how dependent modern infrastructure is on stable environmental conditions. Energy grids, agriculture, transportation, and communications all rely on predictable weather patterns. This dependency increased the perceived strategic leverage of environmental influence. Advances in computing transformed weather from an observational science into a simulation-driven discipline. High-resolution models allowed planners to run scenario analyses, testing how operations would perform under different atmospheric conditions. Even without direct modification, predictive dominance became a strategic asset. Knowing the weather with higher accuracy than an adversary could alter timing and effectiveness. Weather warfare programs ultimately represent a convergence of meteorology and military strategy rather than a single weapon system. Their importance lies in reframing the atmosphere as an operational domain. Instead of being treated as uncontrollable background, weather became something to be measured, modeled, and potentially nudged within narrow limits. Today, the legacy of these programs is visible in the integration of environmental intelligence into nearly every level of military planning. Atmospheric data flows continuously into command systems, influencing decisions in real time. The original ambition of deliberate weather control remains constrained by complexity and risk, but the strategic mindset it produced endures. Weather warfare programs illustrate how modern conflict increasingly considers natural systems as variables of influence. The weapon is not a device, but a method, the attempt to translate environmental knowledge into operational leverage. In that sense, the atmosphere becomes part of strategy itself, quietly shaping outcomes alongside technology and force. AI-controlled battlefield systems. AI-controlled battlefield systems emerged from the steady integration of computation into military operations, evolving from simple automation tools into complex decision support and control architectures. Their development reflects a long trajectory in which warfare increasingly depended on data processing, sensor fusion, and algorithmic coordination rather than solely on human command and mechanical force. The earliest foundations appeared in mid-20th century command and control systems, when militaries began using computers to track aircraft, missiles, and troop movements. These early systems did not make decisions but organized information faster than human staff could manage manually. Even at this stage, strategists recognized that speed of information processing directly influenced battlefield effectiveness. As digital networks expanded in the late Cold War period, battlefield awareness shifted from isolated reports to integrated data pictures. Radar, satellites, reconnaissance aircraft, and ground sensors produced continuous streams of input. The challenge was no longer access to data but coordination of it. This environment created the conditions for algorithmic assistance to move from support into operational influence. Artificial intelligence research accelerated this transition. Machine learning models demonstrated the ability to detect patterns across large datasets, predict outcomes, and recommend actions. Defense institutions began funding programs that applied these capabilities to operational planning, threat detection, and resource allocation. The objective was not to remove commanders, but to enhance their reach and timing. AI-controlled battlefield systems differ from individual autonomous weapons because they operate at the systems level. Instead of guiding a single platform, they coordinate many assets simultaneously: sensors, vehicles, communication nodes, and defensive systems. The battlefield becomes a connected network, with AI managing flows of information and suggested responses across the whole structure. Sensor fusion became a defining feature. AI systems combined visual feeds, radar signals, electronic intelligence, and telemetry into unified operational maps. This integration reduced fragmentation and allowed faster interpretation of complex situations. Human operators received prioritized insights rather than raw streams, compressing the decision cycle. Real-time optimization influenced logistics and positioning. Algorithms calculated supply routes, fuel distribution, maintenance timing, and asset placement with continuous adjustment. This transformed support functions into dynamic systems rather than fixed plans. Efficiency gains at this layer translated directly into operational endurance and flexibility. Simulation also became central. AI-driven battlefield models could run thousands of scenario variations, testing tactical choices before execution. These simulations informed planning by identifying high-probability outcomes and risk concentrations. Command decisions increasingly rested on probabilistic forecasts generated by machine analysis. Communications architecture evolved alongside AI control. Distributed nodes shared data laterally as well as vertically, allowing localized AI agents to act within strategic parameters. This distributed intelligence model reduced dependence on single command centers and increased resilience under disruption. Control became layered rather than centralized. Trust calibration became a formal discipline within deployment. Operators needed to understand when to rely on AI recommendations and when to override them. Interface design, transparency of model reasoning, and confidence scoring became operational requirements. The relationship between human judgment and machine output was engineered deliberately rather than assumed. Strategic doctrine adapted to algorithmic tempo. AI systems operate continuously, without fatigue, and can update assessments instantly as new data arrives. This created a pace mismatch between machine analysis and human deliberation. Military planning adjusted by defining authority thresholds and automated response boundaries to manage the speed differential. Security considerations also shaped system design. Because AI-controlled battlefield networks depend on data integrity, they are sensitive to deception and manipulation. Defensive measures focused on validation, redundancy, and anomaly detection. Protecting the information environment became as important as protecting physical assets. The presence of AI control changed how battlespace complexity is handled. Instead of simplifying the environment to match human limits, systems were built to absorb complexity and present structured choices. This reversed a long-standing constraint in command practice. Complexity became computationally manageable rather than operationally paralyzing. AI-controlled battlefield systems represent a structural transformation rather than a single invention. They shift warfare toward coordinated, adaptive networks guided by continuous analysis. Human command remains present, but increasingly operates through algorithmic mediation. Authority flows through software layers as well as organizational ranks. Today, these systems define the direction of modern military architecture. Their significance lies in orchestration, aligning sensing, movement, defense, and support through machine-managed timing. The battlefield becomes a responsive system rather than a static field of units. Control is expressed through data relationships and algorithmic prioritization. In this model, advantage belongs to the side that integrates perception, computation, and action most seamlessly. AI-controlled battlefield systems embody that integration. They mark the transition from platform-centered warfare to network-centered operations, where intelligence is continuous, coordination is automated, and response is shaped by machine-speed analysis. Space-based weapons platforms. Space-based weapons platforms emerged as a strategic concept soon after humanity first achieved orbital capability. When satellites proved that objects could be reliably placed and maintained above Earth, military planners began evaluating space not only as an observation layer, but as a potential operational domain. Control of orbit promised visibility, timing advantage, and theoretical strike reach across the entire planet. The earliest phase of this thinking developed during the Cold War space race. Initial military use of space focused on reconnaissance and communication. Satellites provided imaging, signals intelligence, and secure links between command structures. These capabilities alone significantly altered strategic balance by reducing uncertainty and improving coordination. Once the value of orbital infrastructure became clear, discussions naturally extended toward whether offensive or defensive weapons could also be stationed there. Early proposals explored orbital bombardment concepts, interceptor satellites, and anti-satellite systems. The logic was grounded in geometry and physics. A platform in orbit passes over vast areas and can observe or reach targets without crossing national borders in the conventional sense. This created a perception of strategic elevation, literal and doctrinal, above terrestrial defenses. Technological limitations initially restrained deployment. Launch costs were extremely high, payload capacity was limited, and on-orbit servicing was minimal. Any weapons platform would need reliable power, targeting accuracy, secure control, and long operational life. These requirements exceeded the capabilities of early space engineering. As a result, most weaponization concepts remained theoretical or experimental. International agreements shaped development paths. Space treaties established principles limiting the placement of certain categories of weapons in orbit, especially weapons of mass destruction. These frameworks did not eliminate military space activity, but they influenced how programs were structured and described. Emphasis shifted toward dual-use systems and defensive justifications. As satellite technology matured, so did platform capability. Improvements in miniaturization, propulsion control, onboard computing, and sensor resolution expanded what orbital systems could do. Precision positioning and timing networks demonstrated that space infrastructure could directly support tactical operations on Earth. This strengthened the argument that space assets were already integral to warfare, even without mounted weapons. Defense research increasingly examined space-based intercept and denial capabilities. Concepts included satellites designed to disable or disrupt other satellites through proximity operations or directed energy. These approaches focused on counterspace control rather than ground attack. The strategic objective was to blind or degrade an adversary's orbital support layer. Power generation remained a defining constraint. Weapons platforms require sustained, controllable energy sources. Advances in solar arrays, energy storage, and thermal regulation gradually improved feasibility. With higher available onboard power, directed energy concepts such as orbital lasers or high-energy emitters became more technically plausible, though still demanding. Targeting accuracy evolved alongside sensing networks. Space-based platforms rely on precise tracking and timing. Integration with global navigation systems and ground sensor grids improved targeting data quality. This interconnected architecture allowed orbital systems to function as nodes within a broader operational network rather than isolated units. Operational doctrine adapted to include space as a contested environment. Instead of viewing orbit as a neutral support layer, planners began treating it as terrain that could be secured, defended, or denied. This conceptual shift influenced force structure and investment priorities. Space control became associated with information superiority and strategic resilience. Space-based weapons platforms also influenced deterrence theory. Assets in orbit are visible in trajectory but difficult to defend once attacked. Their vulnerability created reciprocal restraint dynamics. The risk of escalating disruption to shared orbital infrastructure introduced caution into strategic calculations. Stability depended partly on mutual dependence. Testing and demonstration missions gradually validated enabling technologies without always declaring weapon intent. Maneuverable satellites, rendezvous capabilities, and precision station-keeping proved that complex orbital operations were achievable. Each technical milestone reduced the gap between concept and capability. The psychological dimension of orbital weapon platforms is distinct. A system positioned above the atmosphere suggests reach without proximity and presence without visibility from the ground. This vertical separation changes perception of control and vulnerability. Influence appears to originate from beyond traditional borders and defenses. Today, space-based weapons platforms represent a strategic direction more than a universally deployed reality. Their significance lies in how they redefine high ground. Elevation becomes orbital rather than geographic. Control depends on access, persistence, and precision timing from space. Military power extends into the exoatmospheric layer through infrastructure, sensors, and potentially weaponized nodes. In this framework, space is neither purely civilian nor purely military. It is an operational domain shaped by engineering limits, legal structures, and strategic incentives. Space-based weapons platforms symbolize the continuing expansion of warfare's vertical boundary, from land and sea to air, and now to orbit, where position and energy define influence. HAARP, High-Frequency Active Auroral Research Program. HAARP, the High-Frequency Active Auroral Research Program, originated as a scientific and defense-funded research initiative focused on studying the ionosphere, the electrically charged layer of Earth's upper atmosphere. Established in the early 1990s in Alaska, the program combined radio engineering, atmospheric physics, and space science into a single experimental facility designed to transmit high-frequency radio waves upward and measure how the ionosphere responds. The scientific motivation behind HAARP grew from decades of earlier ionospheric research. Since the beginning of long-range radio communication, engineers understood that the ionosphere plays a crucial role in reflecting and refracting radio waves across great distances. Variations in solar activity, geomagnetic conditions, and atmospheric chemistry could strengthen or disrupt signals. Understanding these dynamics was strategically important for communication reliability, navigation, and radar performance. The HAARP facility was built around a large phased array transmitter field composed of multiple high-frequency antennas operating in coordination. By adjusting phase and timing, researchers could steer and focus radio energy into specific ionospheric regions. The transmitted power density at ground level remained moderate, but when concentrated at altitude, it allowed controlled, localized stimulation of ionospheric particles. Instruments then measured the resulting changes using radar, optical sensors, and signal probes. From a research perspective, HAARP functioned as an active laboratory rather than a passive observatory. Instead of waiting for natural events, scientists could introduce controlled perturbations and observe cause and effect relationships. This experimental method improved understanding of plasma behavior, wave propagation, and upper atmospheric chemistry. The results contributed to models of space weather and signal behavior in disturbed conditions. Defense interest in HAARP was tied to communication resilience and sensing. Military systems depend on reliable high-frequency links and over-the-horizon radar, both of which interact with the ionosphere. By studying how radio energy modifies local ionospheric properties, researchers aim to improve prediction and mitigation of signal disruption. The program therefore aligned with strategic goals of communication continuity under variable space weather conditions. Because HAARP involved powerful transmitters and atmospheric interaction, it attracted public speculation soon after becoming known. The visible antenna field and technical descriptions of ionospheric heating led to interpretations that extended beyond the program's stated scope. The idea that directed radio energy could influence atmospheric behavior became central to many alternative narratives. These interpretations often amplified the scale of effect beyond experimentally supported limits. Technically, HAARP's operational principle is constrained by physics. The ionosphere is vast, dynamic, and driven primarily by solar radiation and geomagnetic forces. HAARP-induced effects are localized and temporary compared to natural variability. Measurements showed small, measurable perturbations useful for study, but not large-scale atmospheric control. Within research documentation, the emphasis remained on diagnostics and modeling rather than environmental manipulation. The program influenced instrumentation and measurement techniques. Sensitive receivers, incoherent scatter radar methods, and optical auroral diagnostics improved through HAARP-linked experiments. These tools enhanced broader geospace science and contributed to international datasets on upper atmospheric behavior. The facility became part of a global network of ionospheric research stations, each contributing complementary observations. Operational control of HAARP shifted over time. Initially funded and managed with defense involvement, it later transitioned toward academic research governance. This administrative evolution reflected changing priorities and the maturation of its scientific output. The facility continued to support experiments, though with more open publication pathways than during its earliest years. Strategically, HAARP shaped how the ionosphere is regarded within defense planning. Rather than being treated as a passive layer, it became understood as an active medium affecting sensing and communication performance. Modeling ionospheric response improved forecasting for signal reliability and radar coverage. The research value lay in predictability rather than control. HAARP also demonstrated the complexity of large-scale scientific infrastructure tied to defense funding. Projects that combine open science with security relevance often generate layered interpretations. Transparency of method does not always prevent speculation about intent. The program became a case study in how advanced research facilities can acquire symbolic meaning beyond their technical function. In the broader trajectory of future-oriented weapons discussion, HAARP represents the category of environmental interaction research rather than a deployed weapon system. Its importance lies in advancing knowledge of a critical atmospheric layer that supports global communication and sensing. The tools it developed enhanced measurement precision and experimental methodology in upper atmospheric science. Today, HAARP stands as a structured research platform focused on ionospheric physics. Its legacy is defined by instrumentation, datasets, and refined models of radio wave interaction with plasma layers. Within strategic analysis, it illustrates how atmospheric knowledge becomes part of defense capability, not through direct force, but through deeper understanding of the medium through which signals and surveillance operate. Ending. The story of future-oriented weapons is, at its core, a story about technology moving faster than public awareness. Some of these systems are real, some experimental, some misunderstood, but all of them reflect how science, defense, and strategy continue to evolve beyond what is immediately visible. Progress in this domain is often quiet, methodical, and layered behind classification, research programs, and long development cycles. Understanding these projects is not about fear, but perspective, seeing how innovation shapes power, security, and the structure of tomorrow's world. If you found this deep dive valuable, support the channel with a like and a subscription. Share your thoughts and interpretations in the comments. Thoughtful discussion makes these topics even more meaningful. And if the episode helped you see the subject from a new angle, share the video with friends who enjoy science, strategy, and hidden technology.